Above you, pressing down with the weight of an ocean you cannot see, stretches an invisible sea of gases 500 kilometers deep, a fluid envelope that wraps the Earth in layers of nitrogen and oxygen, and trace elements moving in current and eddies and vast planetary waves, breathing in rhythms measured not in seconds but in seasons, in years, in the slow turning of climate across millennia. The atmosphere is not empty space but substance, mass, matter. Every square inch of your skin bears the weight of 14 pounds of air pressing down from above, from the column of atmosphere that extends from where you stand to the edge of space. You do not feel this pressure because it is balanced, because the air inside your body pushes outward with equal force, because you were born into this pressure and have never known its absence. But it is there, constant, invisible, the embrace of the sky, the weight of the world's breath resting on your shoulders, on your chest, on every surface that faces upward toward the heavens. The atmosphere is divided into layers, each with its own character, its own temperature profile, its own chemistry. The troposphere, where you live, where weather happens, extends from the surface to about 12 kilometers at the poles, 18 at the equator. Here the air is thick, dense, turbulent, churning with convection. As the sun heats the ground and the ground heats the air, and the warm air rises and the cool air sinks, creating the endless circulation that drives wind, that forms clouds, that brings rain. Temperature decreases with altitude in the troposphere, dropping about 6.5 degrees Celsius for every kilometer you ascend, so that the top of the troposphere, the tropos is, a frigid boundary where temperatures plunge to minus 60 degrees Celsius, where the air is so thin that human lungs cannot extract enough oxygen to sustain consciousness, where the jet streams race at 300 kilometers per hour, rivers of wind that circle the globe. Above the troposphere lies the stratosphere, extending from the tropopause to about 50 kilometers, a realm of stillness, of stability, of air so thin and so cold that weather cannot exist, that clouds cannot form, that the turbulence of the lower atmosphere cannot penetrate. Here temperature increases with altitude, a reversal caused by the presence of ozone, the three-atom form of oxygen that absorbs ultraviolet radiation from the sun, that shields the surface from the DNA-destroying wavelengths that would make complex life impossible. The ozone layer is a gift, a consequence of photosynthesis, of the oxygen released by ancient cyanobacteria billions of years ago, of the slow transformation of the atmosphere from a reducing environment to an oxidizing one, from a poison to a protector. The mesosphere extends from 50 to 85 kilometers, a region where temperature again decreases with altitude, where meteors burn, where the air is so thin that it glows faintly at night with airglow, with the chemiluminescence of atoms and molecules excited by solar radiation during the day and releasing their energy as photons after sunset. The thermosphere above 85 kilometers is where the atmosphere begins to merge with space, where the International Space Station orbits, where auroras dance, where temperature soars to over 1,000 degrees Celsius, not because the air is hot in any meaningful sense, but because the few molecules that exist are moving at tremendous speeds, carrying kinetic energy that would be felt as heat if there were enough molecules to transfer that energy to your skin. The atmosphere is not uniform but textured, layered, structured by temperature gradients, by chemical composition, by the interplay of solar radiation and planetary rotation, and the gravitational pull that holds the gases close to the surface. It is a dynamic system, constantly in motion, constantly exchanging energy with the surface below and the space above, constantly responding to the uneven heating of the sun, to the tilt of the Earth's axis, to the distribution of land and ocean, to the presence of mountains and valleys and ice sheets that shape the flow of air, that create the patterns we call weather, that give each region its climate, its characteristic rhythms of temperature and precipitation and wind. The composition of the atmosphere is remarkably stable at the surface, 78% nitrogen, 21% oxygen, 1% argon and trace gases. But this stability is the result of constant processes, of photosynthesis producing oxygen, of respiration consuming it, of volcanic outgassing releasing carbon dioxide, of weathering of rocks removing it, of the nitrogen cycle converting atmospheric nitrogen into forms that living organisms can use and then returning it to the atmosphere. The atmosphere is not a static reservoir but a living system, intimately connected to the biosphere, to the oceans, to the rocks, to the entire Earth system that regulates temperature, that maintains the conditions for life, that has kept the planet habitable for billions of years despite the increasing luminosity of the sun, despite the impacts of asteroids, despite the eruptions of supervolcanoes. Water vapor, though present in small and variable amounts, is the most important greenhouse gas, the molecule that traps infrared radiation emitted by the Earth's surface, that keeps the planet warm enough for liquid water to exist, for life to flourish. Without water vapor, without the greenhouse effect, the average temperature of the Earth would be minus 18 degrees Celsius, well below the freezing point of water, and the planet would be locked in a permanent ice age, a frozen wasteland where life as we know it could not exist. Water vapor is also the substance of clouds, of precipitation, of the hydrological cycle that moves water from ocean to atmosphere to land and back to ocean, that shapes landscapes, that fills rivers, that sustains ecosystems, that makes the Earth a blue planet, a water world unique in the solar system. The atmosphere is transparent to visible light, allowing the sun's energy to reach the surface, to warm the land and the ocean, to drive photosynthesis, to power the climate system. But it is opaque to much of the infrared radiation emitted by the surface, trapping heat, creating the greenhouse effect that makes the planet habitable. This selective transparency is a consequence of the molecular structure of atmospheric gases, of the way that certain molecules vibrate when struck by photons of certain wavelengths, absorbing the energy, preventing it from escaping to space. Carbon dioxide, methane, nitrous oxide, water vapor, these are the greenhouse gases, the molecules that regulate the Earth's temperature, that determine whether the planet is warm or cold, whether ice sheets advance or retreat, whether sea levels rise or fall. The pressure of the atmosphere decreases exponentially with altitude, dropping by half for every 5.5 kilometers you ascend. At the summit of Mount Everest, at 8,849 meters, the pressure is only 1/3 of what it is at sea level, and the air is so thin that climbers must use supplemental oxygen to avoid hypoxia, to prevent the confusion, the weakness, the loss of consciousness that occurs when the brain is starved of oxygen. At the cruising altitude of commercial aircraft, at 10,000 meters, the pressure is only 1/4 of sea level pressure, and the cabin must be pressurized to simulate an altitude of 2,000 meters, creating an artificial environment where passengers can breathe comfortably, where the pressure differential between inside and outside creates a stress on the fuselage that must be carefully managed, that limits the lifespan of the aircraft, that occasionally fails catastrophically, explosively, fatally. The atmosphere rotates with the Earth, but not uniformly, not rigidly. The surface of the Earth at the equator moves at 1,600 kilometers per hour as the planet spins, and the atmosphere at the surface moves with it, carried along by friction, by the drag of the surface on the air. But as you ascend, as the air becomes thinner, the coupling between surface and atmosphere weakens, and the winds begin to blow relative to the surface, creating the trade winds, the westerlies, the polar easterlies, the global circulation patterns that transport heat from equator to poles, that moderate climate that make the tropics less hot and the poles less cold than they would be without atmospheric circulation. The Coriolis effect, a consequence of the Earth's rotation, deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere, creating the spiral patterns of cyclones and anticyclones, the rotating storms that dominate weather maps, that bring rain and wind and changes in temperature. The Coriolis effect is weak at the equator and strong at the poles, and this gradient shapes the structure of the atmosphere, creates the boundaries between air masses, defines the regions where storms form, where fronts develop, where the atmosphere is most dynamic, most unstable, most likely to produce the dramatic weather events that capture human attention, that inspire awe, that remind us of the power of the invisible ocean above. The atmosphere is ancient, nearly as old as the Earth itself, formed in the first 100 million years after the planet coalesced from the solar nebula 4.5 billion years ago. The original atmosphere was likely hydrogen and helium, the lightest elements, the most abundant in the universe. But these gases were lost to space, stripped away by the solar wind, by the lack of a strong magnetic field, by the planet's relatively weak gravity. The second atmosphere was formed by volcanic outgassing, by the release of water vapor, carbon dioxide, nitrogen, sulfur dioxide from the molten interior, creating a thick, hot, toxic envelope that bore no resemblance to the air we breathe today. The transformation to an oxygen-rich atmosphere took billions of years, required the evolution of photosynthesis, the rise of cyanobacteria, the great oxidation event 2.5 billion years ago, when oxygen levels began to rise, poisoning the anaerobic organisms that had dominated the planet, creating the conditions for the evolution of complex life, of eukaryotes, of multicellular organisms, of the diversity of life that fills the Earth today. The atmosphere is a buffer, a shield, a protective layer that absorbs the impacts of meteoroids, that burns them up in the mesosphere, that prevents most of them from reaching the surface. Every day, the Earth sweeps up about 100 tons of cosmic dust and debris, tiny particles that drift down through the atmosphere, that settle on the surface, that contribute to the sediments, to the slow accumulation of material from space. Larger objects, the size of pebbles or rocks, create meteors, shooting stars, the bright streaks of light that appear when friction with the atmosphere heats the object to incandescence, to temperatures of thousands of degrees, vaporizing the meteor, creating a trail of ionized gas that glows briefly and then fades, leaving nothing but a memory, a wish, a moment of beauty in the night sky. The atmosphere is a medium for sound, for the propagation of pressure waves, for the transmission of vibrations from one place to another. Without atmosphere, there would be no sound, no music, no speech, no rustle of leaves, no crash of waves, no rumble of thunder. Sound travels through air at about 340 meters per second at sea level, slower at higher altitudes where the air is thinner and colder, faster at lower altitudes where the air is denser and warmer. The speed of sound creates the delay between lightning and thunder, the seconds that you count to estimate the distance to the storm, the knowledge that light travels almost instantaneously while sound crawls, taking 5 seconds to cover a mile, allowing you to gauge the approach or retreat of the tempest. The atmosphere is a lens bending light, refracting it, creating mirages, creating the flattened appearance of the sun at sunset, creating the twinkling of stars, the shimmer of heat rising from pavement, the distortions that make distant objects appear closer or farther than they are. The refraction of light in the atmosphere is caused by variations in air density, by temperature gradients, by the way that light slows down slightly when passing through a denser medium, bending toward the normal, creating the optical effects that have fascinated humans for millennia, that have inspired myths, that have challenged scientists, that have revealed the physical properties of the invisible ocean above. And as you rest now, as you feel the weight of the atmosphere pressing gently on your body, as you breathe in the mixture of gases that sustains your life, you can sense the presence of this invisible ocean, this protective envelope, this dynamic system that has shaped the Earth, that has made life possible, that continues to breathe, to circulate, to change, in rhythms that are both immediate and eternal, both local and global, both visible and invisible, in the endless dance of air and energy and water that we call weather, that we call climate, that we call the atmosphere's breath. Clouds are not mere decorations in the sky, not random accumulations of vapor, but structures, architectures, forms, shaped by precise physical laws, by the interplay of temperature and pressure and humidity, by the rising and sinking of air masses, by the invisible currents that sculpt water droplets and ice crystals into the shapes that drift across the heavens, casting shadows on the land below, reflecting sunlight back to space, regulating the temperature of the planet. A cloud is a visible mass of water droplets or ice crystals suspended in the atmosphere, formed when air rises, expands, cools, and reaches the dew point, the temperature at which the air can no longer hold all its water vapor, at which condensation begins, at which invisible vapor becomes visible liquid or solid. The droplets are tiny, typically 10 to 20 micrometers in diameter, small enough to remain suspended by the slightest updraft, by the turbulent motion of the air, drifting slowly downward at a few centimeters per second, taking hours to fall from the base of a cloud to the ground, evaporating long before they reach the surface, unless they collide with other droplets, coalesce, grow large enough to overcome the updrafts, large enough to fall as rain. Clouds are classified by altitude and by form, by their height above the surface, and by their shape, their structure, their appearance. The classification system, developed in the early 19th century by Luke Howard, divides clouds into three basic forms: cumulus, meaning heap, stratus, meaning layer, and cirrus, meaning curl or wisp, and three altitude ranges: low clouds below 2,000 meters, middle clouds between 2,000 and 6,000 meters, and high clouds above 6,000 meters. These basic categories combine to create 10 principal cloud types, each with its own character, its own weather associations, its own beauty. Cumulus clouds are the clouds of fair weather, the puffy white clouds that drift across blue skies on summer afternoons, formed by convection, by the rising of warm air from the sun-heated surface, creating thermals, updrafts, columns of ascending air that cool as they rise, that reach the condensation level and form the flat base of the cumulus cloud, the sharp boundary where invisible vapor becomes visible droplet. The tops of cumulus clouds are rounded, billowing, shaped by the continued rising of air within the cloud, by the turbulence, by the eddies and swirls that give each cloud its unique form, its individual character, its resemblance to cotton, to cauliflower, to castles in the sky. When cumulus clouds grow tall, when the updrafts are strong, when the atmosphere is unstable, they can develop into cumulonimbus, the towering thunderstorm clouds that can reach 15 kilometers high, that punch through the tropopause into the stratosphere, that spread out at the top into the characteristic anvil shape, flattened by the stable air of the stratosphere, by the winds that shear the top of the cloud, that carry ice crystals downwind, creating the anvil that signals the presence of a mature thunderstorm, of lightning and heavy rain and hail and possibly tornadoes, of the most violent weather the atmosphere can produce. Stratus clouds are layers, sheets, blankets of grey that cover the sky, that block the sun, that create the overcast conditions that can persist for days, that bring drizzle, light rain, the damp gloom of a cloudy day. Stratus forms when air is lifted gently, uniformly, over a large area, when a warm air mass slides over a cooler one, when moist air is forced to rise over mountains, when the surface cools at night and the air above it reaches saturation. Stratus clouds are low, often touching the ground as fog, obscuring visibility, creating the eerie conditions where the world disappears into whiteness, where sound is muffled, where distance becomes impossible to judge, where you walk through the cloud feeling the tiny droplets on your face, breathing the saturated air. Cirrus clouds are high, thin, wispy, composed entirely of ice crystals because the temperature at their altitude above 6,000 meters is always below freezing, always cold enough that water cannot exist as liquid, only as solid. Cirrus clouds are delicate, feathery, often appearing as streaks or filaments shaped by the strong winds at high altitude, by the jet streams that stretch them across the sky, that create the mare's tails, the hooked shapes, the patterns that indicate the presence of upper-level winds, that signal changes in the weather that suggest the approach of a warm front, of a low-pressure system, of rain within the next day or two. Altocumulus clouds are middle-level clouds, appearing as patches or layers of white or grey, often arranged in rows, in patterns, in the mackerel sky that resembles the scales of a fish, formed by gentle lifting of air at mid-levels, by waves in the atmosphere, by instabilities that create the regular spacing, the repeating structures, the visual rhythms that make altocumulus one of the most beautiful cloud types, especially at sunrise or sunset, when the low angle of the sun illuminates the clouds from below, painting them in shades of pink and orange and gold, creating the spectacular skies that inspire photographers, that stop people in their tracks, that remind us of the beauty of the atmosphere. Altostratus clouds are middle-level layers, thicker than cirrus, but thinner than stratus, appearing as a uniform grey or blue-grey sheet that covers the sky, that allows the sun to be seen as a dim disk, as a pale circle without distinct edges, without the brightness to cast shadows. Altostratus often precedes a warm front, forms ahead of an approaching low-pressure system, thickens gradually as the front approaches, eventually lowering and becoming nimbus stratus, the rain cloud, the thick dark layer from which steady precipitation falls, from which the sky seems to press down, heavy and oppressive, releasing its moisture in a slow, persistent rain that can last for hours, for days, that soaks the ground, that fills the rivers, that replenishes the aquifers. Stratocumulus clouds are low, lumpy layers, appearing as a field of rounded masses, often covering the entire sky, creating a ceiling, a lid that traps pollution, that holds moisture near the surface, that creates the grey damp conditions common in coastal regions, in areas where cool ocean air moves over warmer land, where the marine layer forms, where the clouds persist through the morning, burning off only when the sun heats the surface enough to break the inversion, to allow the air to mix, to dissolve the cloud layer and reveal the blue sky above. Nimbus stratus is the rain cloud, the thick, dark, featureless layer from which precipitation falls, obscuring the sun completely, creating the dim grey light of a rainy day, the conditions where time seems to slow, where the world becomes quiet, where the sound of rain on roofs and windows becomes the dominant sensation, the rhythmic patter that can be soothing, meditative, conducive to rest, to introspection, to the slowing of pace that rain imposes, that forces you indoors, that creates the cozy feeling of being sheltered, of being safe and dry while the sky releases its burden. Clouds cover about 67% of the Earth's surface at any given time, reflecting about 20% of incoming solar radiation back to space, cooling the planet, offsetting some of the warming from greenhouse gases. Without clouds, the Earth would be significantly warmer, the climate would be more extreme, the temperature difference between day and night would be greater, the poles would be colder and the equator hotter. The habitability of the planet would be reduced. Clouds are a critical component of the climate system, a regulator, a buffer, a mechanism that moderates temperature, that distributes heat, that maintains the conditions for life. The formation of clouds requires not only moisture and cooling, but also condensation nuclei, tiny particles, dust, salt, pollen, pollution, around which water vapor can condense, forming the initial droplets that grow into clouds. In perfectly clean air, in the absence of these nuclei, water vapor can become supersaturated, can exceed 100% relative humidity without condensing, creating a metastable state that persists until a nucleus is introduced, until a surface is provided, until condensation can begin. This is why cloud seeding works, why introducing silver iodide or dry ice into clouds can trigger precipitation, can provide the nuclei that allow supercooled droplets to freeze, to grow, to fall as rain or snow, to release the moisture that the cloud holds but cannot release on its own. The color of clouds depends on their thickness, on the size of the droplets, on the angle of the sun. Thin clouds appear white because they scatter all wavelengths of light equally, reflecting the full spectrum of sunlight. Thick clouds appear grey or dark because they absorb and scatter light multiple times, reducing the amount that reaches the observer, creating the ominous appearance of storm clouds, of cumulonimbus, of the towering structures that block the sun, that cast deep shadows, that signal the approach of severe weather. At sunrise and sunset, when the sun is low on the horizon, when its light passes through a greater thickness of atmosphere, the blue wavelengths are scattered away, leaving the reds and oranges and yellows to illuminate the clouds, to create the spectacular colours that mark the transitions between day and night that have inspired artists and poets for millennia. Lenticular clouds are stationary clouds that form over mountains, shaped like lenses or flying saucers, created by waves in the air as wind flows over a ridge, rising on the upwind side, sinking on the downwind side, creating a series of oscillations of standing waves that persist as long as the wind blows. At the crest of each wave, where the air rises and cools, a cloud forms. In the trough, where the air sinks and warms, the cloud evaporates. The cloud appears stationary, hovering over the mountain, but the air is flowing through it, condensing on the upwind side, evaporating on the downwind side, creating the illusion of a solid object, of a spacecraft, of something that does not belong in the sky, that defies the usual rules of cloud behavior. Mammatus clouds are pouch-like protrusions that hang from the base of a cloud, usually from the anvil of a cumulonimbus, formed by sinking air, by downdrafts, by the descent of ice crystals and rain that cool the air, that make it denser, that cause it to sink, creating the bulges. The udder-like shapes that give Mammatus its name. Mammatus clouds are rare, dramatic, often appearing after a severe thunderstorm, signalling the end of the storm, the dissipation of the updrafts, the transition from violent weather to calm, though their appearance is so unusual, so otherworldly, that they often inspire awe, fear, the sense that something extraordinary is happening in the atmosphere. Noctilucent clouds are the highest clouds, forming at 85 kilometers altitude in the mesosphere, visible only at twilight when the sun has set at the surface, but still illuminates the high atmosphere, creating the eerie electric blue glow of ice crystals at the edge of space. Noctilucent clouds are rare, appearing mostly at high latitudes in summer, formed by water vapor from methane oxidation, by the coldest temperatures in the atmosphere, by the presence of meteoric dust that provides condensation nuclei. They are a recent phenomenon, first observed in the late 19th century, possibly increasing in frequency due to climate change, due to the cooling of the mesosphere warms, creating the conditions for more ice, for more clouds, for more of these ghostly luminous structures that appear in the twilight sky. And as you rest now, as you imagine the clouds drifting above, as you feel the presence of these floating oceans, these architectures of water and ice, you can sense the beauty, the complexity, the endless variety of forms that the atmosphere creates, that the interplay of moisture and temperature and motion produces in shapes that are both familiar and strange, both solid and ephemeral, both heavy with rain and light as air, in the eternal dance of condensation and evaporation, of rising and sinking, of formation and dissolution. That fills the sky with wonder, with beauty, with the visible breath of the earth. Rain is not simply water falling from the sky. not merely the return of moisture to the surface, but a chemical event, a sensory experience, a transformation of the atmosphere that releases compounds, that creates sense, that alters the air in ways that are both measurable and deeply felt, that connect you to the ancient rhythms of the hydrological cycle, to the eternal circulation of water between ocean and sky and land. The smell of rain, that distinctive earthy aroma that rises when the first drops hit dry soil, has a name, Petrichor, from the Greek petra meaning stone, and ichor meaning the fluid that flows in the veins of the gods. Petrichor is not the smell of water itself, which is odorless, but the smell of oils released by plants during dry periods, oils that accumulate on rocks and soil, that are volatilized when raindrops strike the surface, that are carried into the air along with geosmin, a compound produced by soil bacteria, by actinomycetes that release this earthy-smelling molecule when the soil is disturbed, when moisture arrives after drought, when the conditions shift from dry to wet. Geosmin is one of the most potent odorants known, detectable by the human nose at concentrations as low as 5 parts per trillion. A sensitivity that may have evolved because the smell signals the presence of water, the end of drought, the return of conditions favourable for life. The scent of petrichor is not universal, but varies with soil type, with vegetation, with the length of the dry period, with the intensity of the rain, creating a palette of smells that are specific to place, to season, to the particular chemistry of the landscape, that evoke memories, that trigger emotions, that connect you to the land in ways that are primal, visceral, beyond words. Rain begins as ice, even in the tropics, even in summer, because clouds extend high enough that temperatures are below freezing, that water exists as supercooled droplets or ice crystals, that precipitation forms through the collision and coalescence of particles, through the Bergeron process where ice crystals grow at the expense of supercooled droplets, because the vapor pressure over ice is lower than over liquid water, causing water molecules to evaporate from the droplets and deposit onto the crystals, creating snowflakes that fall, that melt as they descend through warmer air, that reach the surface as rain. The size of raindrops varies from the tiny drizzle drops of 0.5 millimeter to the large drops of heavy rain, 5 or 6 millimeters in diameter, flattened by air resistance into the shape of a hamburger bun, not the teardrop shape of popular imagination. Drops larger than 6 millimeters are unstable, break apart as they fall, shatter into smaller drops that continue the descent, that reach the surface as a shower, as a downpour, as the heavy rain that drums on roofs, that creates the white noise that masks other sounds, that fills the air with the sound of water, with the rhythm of precipitation, with the pulse of the storm. The rate of rainfall is measured in millimeters per hour, from the light drizzle of less than 1 millimeter per hour to the heavy rain of 10 millimeters per hour, to the extreme rainfall of tropical storms and hurricanes, where rates can exceed 100 millimeters per hour, where the sky seems to open, where the rain becomes a solid sheet, where visibility drops to near zero, where the sound is deafening, where the water overwhelms drainage systems, flood streets, creates the conditions for flash floods, for landslides, for the catastrophic impacts of too much water arriving too quickly. The distribution of rainfall across the earth is highly uneven, shaped by latitude, by proximity to oceans, by mountain ranges, by atmospheric circulation patterns. The tropics receive the most rain, particularly the equatorial regions where the intertropical convergence zone brings daily thunderstorms, where warm, moist air rises, cools, condenses, releases its moisture in the afternoon rains that are as predictable as the sunrise, that define the rhythm of life in the rainforest, that sustain the incredible biodiversity, the lush vegetation, the ecosystems that thrive on abundant water, on the constant cycling of moisture between soil and atmosphere. The deserts receive the least rain, less than 250 millimeters per year, often much less. creating landscapes where water is the limiting factor, where life is adapted to scarcity, where plants have deep roots, where animals are nocturnal, where the rare rains trigger a burst of activity, of flowering, of reproduction, of life seizing the brief opportunity before the drought returns, before the soil dries, before the water disappears into the ground or evaporates into the air, leaving only the memory of moisture, the promise of the next rain. Monsoons are seasonal reversals of wind direction that bring dramatic changes in rainfall, most famously in South Asia, where the summer monsoon brings torrential rains from June to September, transforming the landscape from brown to green, filling the rivers, replenishing the aquifers, providing the water that sustains agriculture, that feeds over 1 billion people, that makes the Indian subcontinent one of the most densely populated regions on Earth. The monsoon is driven by differential heating of land and ocean, by the way that land heats up faster than water in summer, creating a thermal low over the continent, drawing in moist air from the ocean, creating the conditions for heavy rain, for the seasonal deluge that is both a blessing and a curse, bringing water but also floods, sustaining life but also destroying it. The acidity of rain has changed over the past 2 centuries, shifted from slightly acidic due to dissolved carbon dioxide, which forms carbonic acid, to more acidic due to sulfur dioxide and nitrogen oxides from burning fossil fuels, from industrial processes, from vehicle emissions, creating acid rain with a pH as low as 4, as acidic as vinegar, capable of damaging forests, of acidifying lakes, of dissolving limestone, of corroding buildings and monuments, of altering ecosystems in ways that are subtle but pervasive, that accumulate over decades, that represent one of the unintended consequences of industrialization, of the release of pollutants into the atmosphere without regard for their long-term impacts. The sound of rain is complex, composed of multiple frequencies, from the low rumble of heavy drops hitting the ground to the high-pitched patter of light rain on leaves, creating a soundscape that is rich, textured, variable, that changes with the intensity of the rain, with the surface it strikes, with the presence of wind, with the acoustics of the environment. The sound of rain on a metal roof is different from rain on a tile roof, different from rain on leaves, different from rain on water, each creating its own signature, its own rhythm, its own contribution to the symphony of precipitation. Rain is a cleanser, washing dust and pollen and pollution from the air, from the leaves, from the surfaces, leaving the world fresh, renewed, sparkling in the light that follows the storm. The air after rain is cleaner, clearer, the visibility is better, the colours are more vivid, the sky is a deeper blue, the greens are more intense, the world seems reborn, washed clean, given a fresh start. This cleansing is not just aesthetic but chemical, physical, the removal of particles, the settling of aerosols, the deposition of pollutants onto the surface where they can be absorbed, neutralized, incorporated into the soil, into the water, into the cycles that process and recycle the materials of the earth. The hydrological cycle, the endless circulation of water between ocean and atmosphere and land, is driven by solar energy, by the evaporation of water from the ocean surface, by the transport of water vapor through the atmosphere, by the condensation into clouds, by the precipitation as rain or snow, by the flow of water through rivers back to the ocean, completing the cycle, beginning it again. The cycle is ancient, has been operating for billions of years, has shaped the Earth's surface, has carved valleys, has filled lakes, has created the conditions for life, has maintained the presence of liquid water on the surface despite the changing luminosity of the sun, despite the impacts of asteroids, despite the eruptions of volcanoes. The amount of water in the atmosphere at any given time is small, only about 13,000 cubic kilometers, enough to cover the Earth to a depth of about 25 millimeters, if it all fell at once. But the turnover is rapid. the residence time of water in the atmosphere is only about 9 days, meaning that the entire atmospheric water content is replaced every week and a half, that the water you see as clouds today will be rain tomorrow, will be ocean or soil or plant or animal next week, will be vapor again next month, cycling endlessly, moving through the system, connecting all parts of the earth, linking ocean to land, surface to atmosphere, past to present to future. Rainbows are the optical signature of rain, formed when sunlight enters a raindrop, reflects off the back of the drop, refracts again as it exits, separating into its component colors, into the spectrum from red to violet, creating the arc that appears opposite the sun, that requires both sun and rain, that is a fleeting phenomenon lasting only as long as the conditions persist, as long as the sun shines through the rain, as long as you are positioned correctly to see the light that has been bent and separated and reflected back to your eyes. The intensity of a rainbow depends on the size of the raindrops, with larger drops producing brighter, more vivid rainbows, with smaller drops producing fainter, more washed out arcs. A double rainbow occurs when light reflects twice inside the raindrop, creating a secondary arc outside the primary one, with the colors reversed, with red on the inside and violet on the outside, with the region between the two arcs, Alexander's dark band, appearing darker than the surrounding sky because light is deflected away from this region, creating the contrast that makes the double rainbow so striking, so memorable, so worthy of the awe it inspires. Rain is essential for agriculture, for the crops that feed humanity, for the grains and vegetables and fruits that require water, that depend on the seasonal rains, on the monsoons, on the precipitation that arrives at the right time in the right amounts. That makes the difference between abundance and famine, between prosperity and poverty. The variability of rainfall, the droughts and floods, the years of too much or too little have shaped human history, have driven migrations, have caused the collapse of civilizations, have forced adaptations. Innovations, the development of irrigation, of water storage, of techniques to cope with the uncertainty, with the fundamental dependence of human life on the rhythms of the sky. The future of rainfall is uncertain, changing with the climate, with the warming of the atmosphere, with the increased capacity of warmer air to hold moisture, leading to more intense rainfall events, to heavier downpours, to greater flooding, even as some regions become drier, even as droughts become more severe, more prolonged, creating a world where the extremes are amplified, where the wet get wetter and the dry get drier, where the predictable patterns of the past no longer hold, where adaptation becomes essential, where understanding the chemistry, the physics, the rhythms of rain becomes not just a matter of curiosity, but of survival. And as you rest now, as you imagine the rain falling gently outside, as you hear the soft patter on the roof, as you smell the petrichor rising from the earth, you can feel the connection to this ancient cycle, to the water that has been falling for billions of years, that has nourished life, that has shaped the planet, that continues to fall, to cleanse, to renew in the eternal rhythm of evaporation and condensation, of rising and falling, of the sky giving back to the earth what the earth has given to the sky. In the endless, beautiful, essential dance of rain, snow is frozen silence, crystallized stillness, water transformed into solid geometry, into hexagonal symmetry, into the infinite variety of forms that fall from winter clouds, each flake unique, each a temporary sculpture of ice, a fleeting work of art that exists for moments or hours before melting, before sublimating, before returning to vapor or liquid, completing its brief existence as a visible manifestation of the molecular structure of water. The hexagonal symmetry of snowflakes is a consequence of the molecular structure of water, of the angle between the hydrogen atoms in the H2O molecule, 104.5 degrees, creating a geometry that favors sixfold symmetry, when water molecules arrange themselves into ice crystals. As water vapor deposits onto a freezing nucleus, as molecules add to the growing crystal, they attach at the corners, at the edges, creating branches, creating the dendritic forms, the stellar shapes, the intricate patterns that are determined by temperature and humidity, by the conditions the crystal encounters as it falls through the cloud, as it grows, as it becomes the snowflake that reaches the ground. No two snowflakes are exactly alike, a statement that is almost certainly true given the astronomical number of possible configurations. The countless ways that water molecules can arrange themselves, the infinite variations in the path each crystal takes through the cloud, in the temperature and humidity it encounters, in the precise sequence of growth that creates its unique form. Yet all snowflakes share the hexagonal symmetry, the six-fold pattern that is the signature of ice, the geometric constraint that creates both unity and diversity, both similarity and uniqueness, in the endless variations on a theme. The classification of snow crystals, developed by Wilson Bentley in the early 20th century and refined by Ukichiro and Mikaya, identifies dozens of types based on shape and structure: plates, columns, needles, dendrites, each forming under specific conditions of temperature and humidity. Plates form at temperatures around -2 degrees Celsius, thin hexagonal discs with smooth faces. Columns form at -5 degrees, elongated prisms with hexagonal cross-sections. Dendrites, the classic snowflake shape with 6 branches, form at -15 degrees, growing rapidly in conditions of high humidity, creating the large, intricate crystals that are the most beautiful, the most photographed, the most emblematic of winter. Snow falls slowly, drifting down at 1 to 2 meters per second, taking minutes to descend from cloud to ground, floating on air currents, swirling in eddies, accumulating on surfaces in layers that build with each passing hour, each passing day, transforming the landscape, covering the ground in white, muffling sound, creating the silence that is one of snow's most distinctive qualities. The silence is not absolute, but relative, a reduction in ambient noise caused by the sound-absorbing properties of snow, by the way that the porous structure of the snowpack traps sound waves, prevents them from reflecting, from echoing, creating the quiet that makes a snow-covered landscape feel hushed, peaceful, removed from the noise of the world. The accumulation of snow is measured in depth, in the height of the snowpack, but the amount of water contained in the snow varies with density, with the ratio of ice to air, with the degree of compaction. Fresh snow is light, fluffy, containing as much as 95% air, with a water content of only 5 to 10% by volume. Wet snow is denser, heavier, containing more water, less air, creating the heavy snow that is difficult to shovel, that weighs down branches, that causes roofs to collapse. That represents a significant load, a mass of water temporarily stored as ice, waiting to melt, to flow, to return to the rivers and the ocean. The snowpack in mountains is a reservoir, a storage system that holds water through the winter, that releases it gradually in spring and summer, as temperatures rise, as the snow melts, as meltwater flows into streams and rivers, providing water for agriculture, for cities, for ecosystems downstream. The timing and rate of snowmelt are critical, determining the availability of water, the risk of flooding, the health of rivers, the survival of species that depend on the seasonal pulse of water from the mountains. Changes in snowpack, reductions in snow depth, earlier melting are among the most visible and consequential impacts of climate change, altering the hydrology of entire regions, threatening water supplies, disrupting ecosystems that have evolved with the predictable rhythms of snow accumulation and melt. Avalanches are the sudden catastrophic release of snow from a slope, triggered by the weight of new snow, by changes in temperature, by the presence of a weak layer within the snowpack, by the vibrations from wind or earthquakes or human activity. Avalanches can move at speeds exceeding 200 kilometers per hour, can carry thousands of tons of snow, can bury everything in their path, can destroy forests, buildings, roads, can kill anyone caught in the flow. The study of avalanches, of the conditions that trigger them, of the structure of the snowpack, of the stability of slopes, is essential for safety in mountain regions, for predicting risk, for managing terrain, for saving lives. The albedo of snow, its reflectivity, is among the highest of any natural surface, reflecting 80 to 90% of incoming solar radiation back to space, cooling the surface, creating a feedback loop where snow causes cooling which preserves the snow which causes more cooling. This feedback is one of the mechanisms that can amplify climate change, because as snow cover decreases, as the Earth warms, the darker surfaces beneath the snow, soil, rock, vegetation, are exposed, absorbing more sunlight, warming further, melting more snow, creating a self-reinforcing cycle that accelerates warming, that shifts the climate toward a new state, a warmer state, a state with less snow, less ice, less of the white that reflects the sun's energy back to space. Glaciers are rivers of ice, formed by the accumulation of snow over years, over decades, over centuries, compressing under its own weight, transforming from snow to firn to ice, flowing slowly downhill under the force of gravity, carving valleys, transporting rock, creating the U-shaped valleys, the moraines, the glacial landscapes that cover 10% of the Earth's land surface, that store 70% of the world's fresh water, that are retreating, melting, disappearing in response to warming temperatures, to the change in climate, to the shift in the balance between accumulation and ablation. The cryosphere, the frozen parts of the Earth, snow, ice, glaciers, ice sheets, sea ice, permafrost, is a critical component of the climate system, reflecting sunlight, storing water, regulating sea level, influencing ocean circulation, shaping weather patterns. The cryosphere is changing rapidly, more rapidly than any other component of the Earth system, with Arctic sea ice declining, glaciers retreating, ice sheets losing mass, permafrost thawing, creating feedbacks releasing greenhouse gases, altering albedo, contributing to sea level rise, transforming the planet in ways that are visible, measurable, consequential. Permafrost, ground that remains frozen year-round, underlies 24% of the land surface in the Northern Hemisphere, storing vast amounts of organic carbon, the remains of plants and animals that have been frozen for thousands of years, preserved in the cold, prevented from decomposing. As permafrost thaws, as temperatures rise, this organic matter begins to decompose, releasing carbon dioxide and methane, greenhouse gases that contribute to further warming, creating another feedback loop, another self-reinforcing cycle that amplifies climate change, that accelerates the transformation of the Arctic, of the global climate, of the conditions that have prevailed for millennia. The beauty of snow is undeniable, the way it transforms the landscape, the way it covers imperfections, the way it creates a blank canvas, a fresh start, a world made new. The aesthetic appeal of snow has inspired artists, photographers, poets, has created cultural associations with purity, with peace, with the quiet of winter, with the season of rest, of hibernation, of waiting for spring. But snow is also harsh, unforgiving, deadly to those unprepared, to those caught in blizzards, in whiteouts, in the conditions where visibility drops to zero, where wind and snow combine to create a disorienting, dangerous environment, where survival depends on shelter, on warmth, on the ability to wait out the storm. Blizzards are severe snowstorms characterized by strong winds, heavy snow, low visibility, lasting for at least 3 hours, creating conditions where travel is impossible, where exposure is fatal, where the wind chill can drop temperatures to life-threatening levels. The wind chill is not the actual temperature, but the perceived temperature, the rate at which the body loses heat in the presence of wind, which strips away the thin layer of warm air that surrounds the skin, that insulates the body, forcing the body to work harder to maintain core temperature, to prevent hypothermia, to survive. The silence of the tundra, the vast treeless plains of the Arctic, is profound, absolute, broken only by the wind, by the occasional call of a bird, by the sound of ice cracking, of snow shifting. The tundra is a landscape of extremes, of long winters and short summers, of permafrost and brief blooms of wildflowers, of adaptations to cold, to scarcity, to the challenges of life at the edge of habitability. The tundra is changing, warming faster than any other biome, with shrubs expanding, trees moving north, permafrost thawing, creating a landscape in transition, a landscape that may not resemble the tundra of the past, that may become something new, something different, something that reflects the warming world, the changing climate, the future that is arriving faster than expected, the formation of frost, the delicate ice crystals that form on surfaces when water vapor deposits directly from gas to solid, bypassing the liquid phase, creates patterns, creates feathers and ferns and geometric designs on windows, on leaves, on grass, on any surface that is cold enough. That provides a substrate for the crystals to grow. Frost is ephemeral, disappearing with the first rays of sun, with the warming of the air, sublimating back to vapor, leaving no trace except the memory of its beauty, of its intricate patterns, of the artistry of ice. Hoarfrost is a type of frost that forms in conditions of high humidity and calm air, creating thick deposits of ice crystals, creating the white coating that covers trees, that transforms branches into sculptures, that creates the winter wonderland that is so visually striking, so photogenic, so emblematic of the beauty of winter. Hoarfrost forms when supercooled water droplets in fog freeze onto surfaces, building up layer by layer, creating the rime ice that can grow to several centimeters thick, that can weigh down branches, that can break trees, that can create hazards. But that also creates beauty, creates the conditions for awe, for appreciation of the forms that water can take, of the endless creativity of the atmosphere. And as you rest now, as you imagine the snow falling silently outside, as you feel the stillness, the quiet, the peace of a world covered in white, you can sense the geometry, the symmetry, the crystalline perfection of each flake, the way that water arranges itself into ice, into the hexagonal forms that fall from the sky, that accumulate on the ground, that transform the landscape, that create the silence, the beauty, the frozen stillness of winter. In the eternal cycle of freezing and melting, of solid and liquid, of the water that shapes the world, that sustains life, that falls as snow, as rain, as the endless gift of the sky, high above the weather, above the clouds, above the turbulence of the troposphere, flow rivers of wind, narrow bands of fast-moving air that circle the globe, that steer storms, that transport heat, that connect distant regions in a planetary circulation that operates on scales of thousands of kilometers, that moves at speeds exceeding 300 kilometers per hour, invisible from the surface but profoundly influential, shaping weather patterns, determining the path of hurricanes, guiding the movement of air masses across continents and oceans. The jet streams are located at the boundaries between air masses of different temperatures, at the polar front where cold Arctic air meets warm tropical air, creating a temperature gradient, a difference in pressure, a force that drives the wind, that accelerates the air to speeds that are among the fastest in the atmosphere. The jet streams are not continuous, not uniform, but meandering, undulating, forming waves, forming troughs and ridges, creating the Rossby waves that are the signature of large-scale atmospheric dynamics, that determine where storms will form, where rain will fall, where droughts will persist. There are two main jet streams in each hemisphere, the polar jet and the subtropical jet. The polar jet flows at about 60 degrees latitude, at the boundary between the polar cell and the ferrule cell, at altitudes of 9 to 12 kilometers, varying in position and strength with the seasons. Stronger in winter when the temperature contrast between pole and equator is greatest, weaker in summer when the contrast diminishes. The subtropical jet flows at about 30 degrees latitude, at the boundary between the ferrule cell and the Hadley cell. At slightly higher altitudes, more stable, less variable, but still influential, still shaping weather, still transporting air across the globe. The discovery of the jet streams occurred during World War II, when high-altitude bombers encountered winds so strong that they could barely make progress, that pushed them off course, that revealed the existence of these rivers of air that had been unknown, unsuspected, invisible to observers on the ground. The knowledge of the jet streams transformed aviation, allowed pilots to use tailwinds to reduce flight times, to save fuel, to plan routes that took advantage of the wind, that turned the jet stream from an obstacle into an asset, from a hazard into a resource. The jet stream's influence on weather is profound, determining the path of storm systems, the movement of fronts, the distribution of precipitation. When the jet stream dips south, it brings cold Arctic air into mid-latitudes, creating cold snaps, winter storms, conditions that are unseasonably cold, that disrupt normal patterns, that create the variability that characterizes weather in the temperate zones. When the jet stream shifts north, it allows warm air to move poleward, creating heat waves, droughts, conditions that are unseasonably warm, that stress ecosystems, that create the extremes that are becoming more common as the climate changes, as the Arctic warms, as the temperature gradient that drives the jet stream weakens. The speed of the jet stream varies with the strength of the temperature gradient, with the difference in temperature between the air masses on either side of the jet. A strong gradient creates a strong jet, with winds exceeding 400 kilometers per hour, creating a narrow, fast-moving river of air. A weak gradient creates a weak jet, with winds of 100 to 200 kilometers per hour, creating a broader, slower-moving flow. The strength of the jet influences the weather, with a strong jet creating more vigorous storms, more rapid changes, more dynamic conditions, and a weak jet creating more persistent patterns, more blocking, more stagnation, more of the conditions that can lead to prolonged droughts or prolonged rains. The meandering of the jet stream, the formation of Rossby waves, is driven by the interaction of the jet with mountains, with land-sea contrasts, with the rotation of the Earth, creating waves that propagate around the globe, that influence weather thousands of kilometers downstream, that create teleconnections, links between distant regions, patterns where conditions in one part of the world influence conditions in another, where a drought in one region is connected to floods in another, where the atmosphere operates as a single, integrated system, where local weather is influenced by global patterns. The jet stream transports not only air but also moisture, heat, momentum, energy, creating the conditions for storm development, for the intensification of cyclones, for the formation of the low-pressure systems that bring rain and wind and changes in temperature. The jet stream is the highway along which storms travel, the path that determines whether a storm will affect your region or pass to the north or south, whether you will experience the rain or the clear skies, whether the weather will change or remain the same. The polar vortex, a large area of low pressure and cold air surrounding the poles, is related to the jet stream, with the polar jet forming at the boundary of the vortex, at the edge where cold polar air meets warmer mid-latitude air. When the polar vortex is strong, when the temperature contrast is large, the jet stream is fast, tight, circular, keeping the cold air confined to high latitudes. When the polar vortex weakens, when the temperature contrast diminishes, the jet stream becomes wavy, meandering, allowing cold air to spill southward, creating the polar vortex events that bring extreme cold to mid-latitudes, that create the conditions for severe winter weather, for the cold snaps that disrupt normal life, that challenge infrastructure, that test the limits of human adaptation to cold. The jet stream is changing, weakening, becoming more wavy, more prone to blocking patterns. As the Arctic warms faster than the rest of the planet, as the temperature gradient between pole and equator diminishes, as the conditions that have driven the jet stream for millennia shift, creating a new climate regime, a new pattern of atmospheric circulation, a new normal that is still emerging, still uncertain, still the subject of intense research, of debate, of efforts to understand how the change in jet stream will influence weather, will influence climate, will influence the future. Clear air turbulence, the sudden unpredictable jolts that aircraft encounter at high altitudes, is often associated with the jet stream, with the wind shear, the rapid change in wind speed and direction that occurs at the edges of the jet, creating instabilities, creating turbulence that is invisible. That cannot be detected by radar, that can only be avoided by understanding the structure of the jet, by predicting where the shear will be strongest, by routing flights to avoid the regions of greatest turbulence. The increasing frequency of clear air turbulence is one of the predicted consequences of climate change, of the changing jet stream, of the increased wind shear that comes with a more variable, more wavy jet. The jet stream also influences the dispersal of pollutants, of volcanic ash, of smoke from wildfires, transporting these materials across continents, across oceans, creating air quality issues thousands of kilometers from the source, creating the conditions where pollution from one country affects another, where the atmosphere does not respect borders, where the consequences of emissions are global, not local, where the interconnectedness of the atmosphere becomes visible, tangible, consequential. The study of the jet stream involves satellites, weather balloons, aircraft observations, computer models, all working together to map the wind, to understand its structure, to predict its behavior, to forecast the weather that it will bring. The jet stream is one of the most important features of the atmosphere, one of the key determinants of weather, one of the elements that must be understood, must be predicted, must be monitored to provide accurate forecasts, to warn of severe weather, to protect lives and property. The jet stream is also a source of potential energy, of wind power that could be harnessed, that could be captured by high-altitude wind turbines, by kites, by systems that tap into the fast, persistent winds that flow at jet stream altitudes. The technical challenges are significant, the costs are high, but the potential is enormous. The possibility of accessing a renewable energy source that is vast, that is constant, that could provide power on a scale that dwarfs current wind energy production, that could transform the energy landscape, that could contribute to the transition away from fossil fuels toward a sustainable energy future. The seasonal migration of the jet stream is one of the most predictable features of atmospheric circulation, shifting northward in summer as the temperature contrast between pole and equator weakens, shifting southward in winter as the contrast strengthens, creating the annual rhythm that determines the climate zones, that defines the boundaries between temperate and tropical, between wet and dry, between the regions that receive winter rain and those that receive summer rain. This migration is not uniform, not smooth, but varies from year to year, creating the variability that makes weather forecasting challenging, that creates the surprises, the unexpected cold snaps in spring, the unseasonable warmth in autumn, the deviations from the average that are the essence of weather. The jet stream can split, can divide into two or more branches, creating complex patterns, creating multiple pathways for storms, creating the conditions where weather becomes unpredictable, where forecasts become uncertain, where the atmosphere reveals its chaotic nature, its sensitivity to small perturbations, its tendency to create patterns that are both orderly and random, both structured and chaotic. The split jet creates blocking patterns, creates regions of high pressure that persist for weeks, that divert storms, that create droughts in some regions and floods in others, that demonstrate the power of the jet stream to shape weather on continental scales. The nocturnal low-level jet is a different phenomenon, occurring at lower altitudes, typically 500 to 1,000 meters above the surface, forming at night when the surface cools, when the friction between the surface and the air decreases, allowing the wind to accelerate, creating a river of air that flows through the night, that transports moisture, that creates the conditions for nighttime thunderstorms, for the nocturnal convection that is common in the Great Plains of North America. In other regions where the geography and the climate create the right conditions for this low-level jet to form, to persist, to influence the weather in ways that are distinct from the upper-level jet streams. The African easterly jet is a mid-level jet stream that flows from east to west across Africa during summer, created by the temperature contrast between the hot Sahara Desert and the cooler, more humid regions to the south, driving the formation of African easterly waves. The atmospheric disturbances that move westward across the Atlantic, that are the seeds of tropical storms, of hurricanes, of the powerful cyclones that form in the tropical Atlantic, that threaten the Caribbean, that impact the southeastern United States, that demonstrate the global connections, the way that weather in one region influences weather thousands of kilometers away, the way that the jet streams, both high and low, both tropical and polar, are part of a single integrated atmospheric system. The relationship between jet streams and ocean currents is complex, bidirectional, with the atmosphere influencing the ocean and the ocean influencing the atmosphere, creating coupled patterns, creating oscillations like the El Niño Southern Oscillation, the North Atlantic Oscillation, the Pacific Decadal Oscillation, patterns that persist for months or years, that influence weather and climate across entire ocean basins, across entire continents, that create the long-term variability that is distinct from day-to-day weather, that shapes the climate on timescales of seasons, of years, of decades. The jet stream responds to these ocean patterns, shifts its position, changes its strength, creating teleconnections, creating the links between distant regions that make climate prediction possible, that allow forecasters to anticipate conditions months in advance, to provide early warnings of droughts, of floods, of the climate anomalies that can have profound impacts on agriculture, on water resources, on societies. The jet stream's role in the formation of extratropical cyclones, the mid-latitude storms that bring most of the precipitation to temperate regions, is central, essential, the mechanism by which energy is transferred from the tropics to the poles, by which heat is redistributed, by which the temperature gradient is maintained despite the uneven heating of the sun. The cyclones form along the jet stream, at the locations where the jet creates divergence aloft, where air is removed from the upper atmosphere, creating a vacuum, creating low pressure at the surface, drawing in air, creating the circulation, the counterclockwise flow in the northern hemisphere, the clockwise flow in the southern hemisphere, the spiral patterns that are visible on satellite images, that are the signature of the storm, of the weather system that brings clouds and rain and wind and changes in temperature. The jet stream also influences the tracks of hurricanes, the paths that tropical cyclones follow as they move away from the tropics, as they curve northward, as they are captured by the mid-latitude flow, by the jet stream that steers them, that determines whether they will make landfall or curve out to sea, whether they will intensify or weaken, whether they will bring destruction or dissipate harmlessly over the ocean. The interaction between the tropical cyclone and the jet stream is complex, with the jet providing wind shear that can tear the storm apart, that can prevent intensification, or providing an outflow channel that allows the storm to strengthen, that creates the conditions for rapid intensification, for the explosive development that can turn a tropical storm into a major hurricane in a matter of hours. The study of jet stream dynamics has revealed the existence of jet streaks, regions within the jet where the wind is particularly strong, where the flow is accelerated, creating zones of enhanced divergence and convergence, creating the preferred locations for storm development, for the rapid intensification of cyclones, for the formation of severe weather. These jet streaks move along the jet stream, propagate around the globe, create the transient features that make weather forecasting challenging, that require constant monitoring, constant updating of forecasts, constant vigilance to detect the changes, the shifts, the developments that can turn a quiet day into a stormy one, that can bring unexpected weather, unexpected impacts, unexpected challenges. The future of the jet stream is uncertain, tied to the future of the climate, to the warming of the Arctic, to the melting of sea ice, to the changes in temperature gradients that are the fundamental drivers of atmospheric circulation. Some models predict a weaker, more meandering jet stream, creating more persistent weather patterns, more blocking, more extremes. Other models predict different outcomes, different patterns, different futures, reflecting the complexity of the climate system. The difficulty of predicting how all the components will interact, how the feedbacks will play out, how the atmosphere will respond to the unprecedented changes that are underway, that are transforming the planet, that are creating a new climate, a new atmospheric circulation, a new jet stream that may behave in ways that are different from the past, that may create weather patterns that are unfamiliar, that may challenge our ability to adapt, to cope, to thrive in a changing world. The jet stream is a reminder of the scale of atmospheric processes, of the way that the atmosphere operates on planetary scales, connecting regions, transporting air, creating the patterns that we experience as weather, as climate, as the conditions that shape our lives, that determine where we can live, what we can grow, how we must adapt. The jet stream is invisible, but its effects are everywhere, in the storms that cross the oceans, in the cold snaps that grip the continents, in the heat waves that bake the land, in the endless circulation of air that is the breath of the planet, the pulse of the atmosphere, the river that flows above, unseen but ever present, shaping the world below. And as you rest now, as you imagine the jet stream flowing high above, as you sense the movement of air on scales that dwarf human experience, you can feel the connection to this planetary circulation, to the winds that circle the globe, that transport heat and moisture and energy, that create the weather, that shape the climate, that are part of the vast interconnected system that is the Earth's atmosphere, flowing, changing, adapting in the eternal dance of air and energy, of heat and cold, of the invisible river that flows above, guiding the storms, steering the weather, connecting the world in the silent, powerful current of the jet stream. The sky is not always blue, not always grey, but sometimes painted in colours that seem impossible, that defy the ordinary, that transform the atmosphere into a canvas of light, of refracted sunbeams and scattered photons and excited atoms, creating the luminous phenomena that have inspired wonder, that have sparked myths, that reveal the physics of light interacting with air, with water, with the magnetic field of the Earth. The blue of the sky is a consequence of Rayleigh scattering, the process by which molecules of nitrogen and oxygen scatter sunlight, preferentially scattering the shorter wavelengths, the blues and violets, in all directions, filling the sky with blue light, while the longer wavelengths, the reds and oranges and yellows, pass through relatively unscattered, reaching your eyes directly from the sun. The sky appears blue because you are seeing the scattered light, the light that has been redirected by the molecules of air, that comes from all directions, that creates the dome of blue that arches overhead, that is brighter near the horizon where the path through the atmosphere is longer, where more scattering occurs, where the blue deepens, intensifies, becomes the rich azure of a clear day. At sunset and sunrise, when the sun is low on the horizon, when its light must pass through a greater thickness of atmosphere, the blue light is scattered away completely, scattered out of the line of sight, leaving only the reds and oranges and yellows to reach your eyes, to paint the sky in the warm colours of twilight, to create the spectacular displays that mark the transitions between day and night, that have been celebrated in art, in poetry, in the quiet moments of watching the sun sink below the horizon, watching the colours fade, watching the stars emerge. Twilight is not instantaneous but gradual, divided into 3 phases. Civil twilight, when the sun is less than 6 degrees below the horizon, when there is enough light to see clearly, to read, to work. Nautical twilight, when the sun is between 6 and 12 degrees below the horizon, when the horizon is still visible, when navigation by stars becomes possible. And astronomical twilight, when the sun is between 12 and 18 degrees below the horizon, when the sky is dark enough for astronomical observations, for seeing faint stars, for experiencing the full depth of the night sky. The duration of twilight varies with latitude, longer at high latitudes, where the sun's path is more oblique, where the transition from day to night is stretched out, where summer nights never fully darken, where the sun hovers just below the horizon, creating the white nights of the Arctic, the midnight sun of the polar regions. Rainbows are arcs of colour formed by the refraction and reflection of sunlight in raindrops, requiring both sun and rain, requiring the observer to be positioned with the sun behind them and rain in front, creating the geometry that allows the refracted light to reach the eyes, to create the spectrum, to separate white light into its component colours. The primary rainbow appears at an angle of 42 degrees from the antisolar point, the point directly opposite the sun, with red on the outside and violet on the inside. The order determined by the wavelength-dependent refraction of light, by the way that red light bends less than violet light, creating the familiar sequence of colours that spans the sky. The secondary rainbow, fainter than the primary, appears at 51 degrees from the antisolar point, formed by light that reflects twice inside the raindrop, creating a reversed spectrum, with violet on the outside and red on the inside. With the region between the 2 rainbows, Alexander's dark band, appearing darker than the surrounding sky because light is deflected away from this region, creating the contrast that makes the double rainbow so striking, so memorable, so rare and beautiful, that it inspires awe, that makes people stop, that creates moments of shared wonder. Supernumerary rainbows are faint, closely spaced bands of colour that sometimes appear just inside the primary rainbow, caused by interference, by the wave nature of light, by the way that light waves from different paths through the raindrop can add or cancel, creating the alternating bright and dark bands, the pastel shades of pink and green and violet that are delicate, ephemeral, visible only when conditions are perfect, when the raindrops are uniform in size, when the observer is positioned precisely, when the atmosphere cooperates to create this subtle, exquisite phenomenon. Halos are rings of light that appear around the sun or moon, formed by the refraction of light through ice crystals in cirrus clouds, in the high, thin clouds that are composed entirely of ice that act as prisms, bending light, creating the circular halo at 22 degrees from the sun. The most common halo and the rarer 46-degree halo, both caused by the hexagonal structure of ice crystals, by the angles at which light enters and exits the crystal, by the geometry that determines the path of the refracted light. Halos are often accompanied by sundogs, bright spots that appear on either side of the sun, at the same elevation, caused by plate-shaped ice crystals that are oriented horizontally, that refract light preferentially in certain directions, creating the mock suns, the parphelia, that flank the real sun, that create the illusion of 3 suns in the sky. Auroras are the light shows of the polar regions, the curtains of green and red and purple that dance across the night sky, caused by charged particles from the sun, from the solar wind, that are funneled by the Earth's magnetic field toward the poles, that collide with atoms and molecules in the upper atmosphere, that excite them, that cause them to emit light, creating the aurora borealis in the north and the aurora australis in the south. The green light, the most common color, is emitted by oxygen atoms at altitudes of 100 to 300 kilometers. The red light, rarer, is emitted by oxygen at higher altitudes above 300 kilometers. The purple and blue light is emitted by nitrogen, creating the complex shifting patterns, the waves and arcs and rays that move across the sky, that respond to changes in the solar wind, to fluctuations in the magnetic field, to the dynamic interaction between the sun and the earth. The intensity of auroras varies with solar activity, with the 11-year solar cycle, with the occurrence of solar flares and coronal mass ejections that send bursts of charged particles toward Earth, that create geomagnetic storms, that intensify the auroras, that push them to lower latitudes, that make them visible from regions where they are normally never seen. The most intense auroras can disrupt radio communications, can interfere with satellite operations, can induce currents in power grids, can create the conditions for blackouts, for the technological vulnerabilities that come with our dependence on electricity, on electronics, on systems that are sensitive to the electromagnetic environment. The green flash is a rare optical phenomenon that occurs at sunset or sunrise, when the sun is just at the horizon, when atmospheric refraction separates the light into its component colors, with the green wavelength appearing briefly, for a second or two, as the last or first color visible, creating the flash of green that is so brief, so rare, that it has inspired legends, that has been sought by sailors, by photographers, by anyone who has heard of it and wants to witness it, to see the green that appears and disappears in an instant, that requires clear skies, a distant horizon, and the patience to watch the sunset, to wait for the moment, to hope that conditions are right. Crepuscular rays are the beams of sunlight that appear to radiate from the sun, that stream through gaps in clouds, that create the God rays, the shafts of light that seem to descend from the heavens, that are actually parallel rays made to appear convergent by perspective, by the way that parallel lines appear to meet at a distant point, creating the illusion of radial beams, of light emanating from a source, of the sun reaching down to touch the earth. The rays are made visible by scattering, by the way that dust and water droplets in the air scatter the light, creating the visible beams, the contrast between the illuminated air and the shadowed air, the dramatic effect that has been captured in countless photographs, that has inspired religious imagery, that connects the physical phenomenon to the metaphysical, to the sense of the divine, to the feeling that the sky is speaking, is revealing something, is offering a glimpse of the transcendent. Anti-crepuscular rays are the continuation of crepuscular rays, appearing on the opposite side of the sky from the sun, converging toward the antisolar point, creating the illusion that the rays are curving across the entire dome of the sky, that they are wrapping around the atmosphere, when in reality they are still parallel, still straight, made to appear convergent by the same perspective effect that creates crepuscular rays. These rays are rarer, more subtle, requiring clear skies and the right conditions of dust and moisture to make them visible, creating the sense that the entire sky is structured by light, by the geometry of the sun's position, by the invisible architecture of illumination. The belt of Venus is a pink or reddish band that appears above the horizon opposite the setting sun, just above the dark blue shadow of the Earth, created by the backscattering of reddened sunlight by the atmosphere, by the way that the light from the sunset, already filtered through the atmosphere, is scattered back toward the observer, creating the soft pastel glow that appears in the minutes after sunset, that fades as the sun sinks deeper below the horizon, that is one of the most delicate, most overlooked phenomena of twilight, visible to anyone who looks east as the sun sets in the west, who takes the time to observe not just the sunset but the entire sky, the full panorama of color that twilight creates. The purple light, a phenomenon distinct from the belt of Venus, appears as a purple or magenta glow in the western sky during twilight, caused by the combination of red light from the setting sun and blue light scattered by the atmosphere, creating a color that is neither purely red nor purely blue, but a mixture, a synthesis, a hue that appears only during the brief window when the sun is at a specific angle below the horizon, when the atmospheric conditions are right, when the observer is positioned to see the overlap of the scattered blue and the transmitted red, creating the purple that has been noted by observers for centuries, that has been studied by atmospheric scientists. That remains one of the more mysterious, more beautiful aspects of twilight. Light pillars are vertical columns of light that appear above or below the sun or moon, or bright artificial lights, caused by the reflection of light from ice crystals that are falling through the air, that are oriented horizontally, that act as tiny mirrors reflecting the light upward or downward, creating the pillar, the shaft of light that seems to extend from the light source, that can reach high into the sky, that is most commonly seen in cold climates, in winter, when ice crystals are present in the lower atmosphere, when the conditions are right for these crystals to form, to fall, to create the optical effect that transforms a simple light into a beacon, into a column that reaches toward the heavens. The circumzenithal arc, sometimes called the upside-down rainbow, is a colourful arc that appears high in the sky above the sun, with red on the bottom and violet on the top, the reverse of a rainbow, formed by the refraction of sunlight through horizontally oriented plate-shaped ice crystals in cirrus clouds, creating an arc that is brighter, more vivid than a rainbow, but also rarer, more fleeting, visible only when the sun is at a low angle, when the ice crystals are present, when the observer happens to look up to notice the arc of colour overhead, the smile in the sky, the phenomenon that is so beautiful, so unexpected, that it stops people in their tracks, that creates moments of pure wonder. Moonbows, or lunar rainbows, are rainbows formed by moonlight rather than sunlight, appearing as faint, colourless arcs, because the light from the moon is too dim to activate the colour receptors in the human eye, creating a ghostly, ethereal bow that is visible only on nights when the moon is full or nearly full, when rain is falling opposite the moon, when the sky is dark enough that the faint light of the moon bow can be seen, when the observer is fortunate enough to be in the right place at the right time to witness this rare, beautiful phenomenon that has been recorded in myths, in legends, in the stories of cultures around the world. The colour of the sky varies not only with time of day, but also with altitude, with the amount of atmosphere above the observer. At high altitudes in the mountains, the sky is a deeper blue, almost violet, because there is less atmosphere to scatter the light, less air to create the pale blue of lower elevations. At the edge of space, from the perspective of astronauts, the sky is black, because there is no atmosphere to scatter the light, because the scattering that creates the blue sky requires air, requires molecules, requires the medium that is absent in the vacuum of space. The gradient from pale blue at sea level to deep blue in the mountains to black in space is a reminder of the atmosphere's presence, of its role in creating the sky, of the way that what we see is not the absence of light, but the scattering of light, the interaction of photons with molecules, the physics that creates the dome of colour above. The intensity of sky colours is affected by pollution, by aerosols, by the particles suspended in the air that scatter light, that can enhance sunsets, making them more vivid, more colourful, or that can dull the sky, making it hazy, making the blue less pure, making the atmosphere less transparent. The most spectacular sunsets often occur after volcanic eruptions, when the stratosphere is filled with sulfate aerosols, when the particles scatter the light in ways that create the intense reds and oranges and purples, the colours that persist for months, for years. Thus are the atmospheric legacy of the eruption, the beauty born from catastrophe, the reminder that the atmosphere is a dynamic system, constantly changing, constantly responding to inputs from below, from the earth, from the volcanoes and the fires and the human activities that release particles into the air. The study of atmospheric optics, of the way that light interacts with the atmosphere, has revealed the complexity, the beauty, the endless variety of phenomena that can occur, that depend on the precise conditions of temperature and humidity and particle size and sun angle and observer position, creating a field of study that is both scientific and aesthetic, both quantitative and qualitative, both about understanding the physics and appreciating the beauty, about measuring the wavelengths and experiencing the wonder, about explaining the mechanisms and preserving the mystery, the sense that the sky is not just a physical system but a source of inspiration, of awe, of the feeling that the world is more beautiful, more complex, more worthy of attention than we often realize. The colors of the sky at different times of day, in different weather conditions, in different seasons, create a palette that is endlessly variable, endlessly beautiful, endlessly capable of surprising, of delighting, of creating moments where you stop, where you look up, where you appreciate the atmosphere not as a functional system, not as the medium for weather, but as a source of beauty, as a canvas for light, as a reminder that the world is full of wonder, that the ordinary can become extraordinary, that the sky is always there, always changing, always offering something new to see, to experience, to remember. And as you rest now, as you imagine the sky painted in colors, as you see the rainbows and the auroras and the twilight glow, you can feel the beauty, the physics, the light that fills the atmosphere. That creates the luminous phenomena that have inspired humanity for millennia, that continue to inspire, that remind us that we live beneath a sky that is not just air, not just weather, but a realm of light, of color, of beauty, that is always there, always waiting to be seen, to be appreciated, to be experienced in the quiet moments when you look up, when you pause, when you allow yourself to be filled with wonder at the luminous sky. Before the thunder, before the lightning, before the storm breaks and the rain begins, there is a tension in the air, a charge building, a separation of positive and negative, an electric field growing stronger, invisible but palpable, felt as the prickling of skin, as the standing of hairs on end, as the sense that something is about to happen, that the atmosphere is preparing to release its energy in a flash of light, in a crack of sound, in the violent discharge that is lightning. Thunderstorms are the most common severe weather phenomenon, occurring about 2,000 times simultaneously around the world at any given moment, producing about 100 lightning strikes per second globally, creating a continuous electrical activity that is part of the global electric circuit, that maintains the charge separation between the Earth's surface and the ionosphere, that is essential for the electrical environment of the planet. Each thunderstorm is a heat engine, converting the latent heat of water vapor into kinetic energy, into the updrafts and downdrafts that characterize the storm, into the turbulence that separates charge, that creates the conditions for lightning. The formation of a thunderstorm requires 3 ingredients: moisture, instability, and lift. Moisture provides the fuel, the water vapor that will condense, releasing latent heat, powering the updrafts. Instability means that the atmosphere is prone to vertical motion, that a parcel of air, once lifted, will continue to rise, will accelerate upward, creating the strong updrafts that are the signature of a thunderstorm. Lift is the mechanism that initiates the motion, that gets the air moving upward. That can come from heating of the surface, from the convergence of winds, from the lifting of air over mountains, from the passage of a front, from any process that forces air to rise, to cool, to condense, to begin the cycle of convection that builds the storm. The life cycle of a thunderstorm has 3 stages: the developing stage, the mature stage, and the dissipating stage. In the developing stage, the updraft dominates. Warm, moist air rises, cools, condenses, forms the cumulus cloud that grows taller, that builds vertically, that reaches higher and higher into the atmosphere. In the mature stage, precipitation begins to fall. creating a downdraft, creating the coexistence of updraft and downdraft, creating the most intense phase of the storm, the phase when lightning is most frequent, when rain is heaviest, when hail may form, when tornadoes may develop. In the dissipating stage, the downdraft dominates, cutting off the supply of warm, moist air, starving the updraft, causing the storm to weaken, to spread out, to transition from a towering cumulonimbus to a spreading anvil, to the remnants of the storm that drift downwind, that eventually evaporate, that return the moisture to the atmosphere, completing the cycle. Lightning is a massive electrical discharge, a current of tens of thousands of amperes flowing between cloud and ground, or between different parts of the cloud, or between cloud and air, heating the air to temperatures exceeding 30,000 degrees Celsius, 5 times hotter than the surface of the sun, creating a channel of plasma, of ionized gas, that glows with the intense white light of the lightning bolt. The heating is so rapid, so extreme, that it creates a shock wave, an expansion of air that propagates outward as sound, as the thunder that follows the lightning, that rumbles and cracks and echoes, that can be heard for kilometers, that signals the presence of the storm, that warns of the danger. The time delay between lightning and thunder is a measure of distance, with sound traveling at about 340 meters per second, taking about 3 seconds to travel 1 kilometer, allowing you to estimate how far away the lightning struck, how close the storm is, whether it is approaching or receding. If the delay is decreasing, the storm is approaching. If the delay is increasing, the storm is moving away. If you see the lightning and hear the thunder simultaneously, the lightning is very close, dangerously close, and you should seek shelter immediately, should avoid open areas, should stay away from trees, from metal objects, from anything that could conduct the current, that could make you a target for the next strike. The mechanism of charge separation in thunderstorms is complex, not fully understood, but involves the collision of ice particles, the interaction of graupel, soft hail, with ice crystals, with the graupel becoming negatively charged and the ice crystals becoming positively charged, with the heavier graupel falling to the lower part of the cloud, and the lighter ice crystals being carried to the upper part by the updraft, creating a separation of charge, creating a vertical electric field, creating the conditions for lightning. The ground beneath the storm becomes positively charged by induction, creating a potential difference, creating the electric field that will eventually break down, that will create the conductive path, that will allow the current to flow, that will create the lightning. Lightning begins with a stepped leader, a channel of ionized air that propagates downward from the cloud in steps, in discrete jumps, creating a path of least resistance, branching, searching for the ground, invisible to the eye, moving at speeds of about 100,000 kilometers per second, taking about 20 milliseconds to reach the ground. When the stepped leader connects with the ground, or with an upward stream arising from the ground, the circuit is complete and the return stroke occurs, a massive surge of current flowing upward from the ground to the cloud, creating the bright flash that we see as lightning that lasts for only a few microseconds, but that carries most of the energy, most of the current, most of the light. Cloud to ground lightning is the most dangerous, the most studied, but it represents only about 25% of all lightning. The majority of lightning occurs within the cloud, between the positive and negative charge centers, creating the intracloud lightning, the sheet lightning that illuminates the cloud from within, that creates the diffuse glow, the flickering that is visible even when the bolt itself is hidden. That is less dangerous to people on the ground, but that is still part of the electrical activity, still part of the energy release, still part of the storm. Thunder is not a single sound but a complex acoustic event, composed of multiple frequencies, from the low rumble of distant thunder to the sharp crack of nearby thunder, shaped by the length of the lightning channel, by the distance to the observer, by the reflections and refractions of sound waves in the atmosphere, by the temperature and humidity and wind, creating a soundscape that is unique to each storm, to each lightning strike, to each moment of the storm's life. The rumble is caused by the fact that different parts of the lightning channel are at different distances from the observer, so the sound arrives at different times, creating the prolonged rumble, the rolling thunder that can last for many seconds, that can echo off clouds, off mountains, off buildings, creating the complex reverberating sound that is one of the most distinctive features of a thunderstorm. The energy released by a single lightning strike is enormous, about 1 billion joules, equivalent to the energy in about 250 kilowatt hours of electricity, enough to power a typical home for about a week. But the duration is so brief, the power so concentrated, that it is difficult to capture, difficult to harness, difficult to use, making lightning an impressive display of natural power but not a practical source of energy. The energy goes into heating the air, creating the shock wave, creating the light, creating the electromagnetic radiation that can be detected by radio receivers, that can interfere with electronics, that can damage sensitive equipment. That is part of the electromagnetic environment of the Earth. Lightning strikes the Earth about 100 times per second, about 8 million times per day, about 3 billion times per year, creating a continuous electrical activity that is part of the global electric circuit that maintains the negative charge of the Earth's surface. That balances the positive charge of the ionosphere, that creates the electric field that exists even in fair weather, that is about 100 volts per meter near the surface, that decreases with altitude, that is part of the electrical environment in which we live, in which all life exists, that is influenced by thunderstorms, by lightning, by the continuous discharge of the atmosphere. The danger of lightning is real, with about 24,000 deaths per year globally, with many more injuries, with damage to property, to infrastructure, to forests, to anything that can be struck, that can conduct the current, that can be damaged by the heat, by the shock wave, by the electromagnetic pulse. The risk can be reduced by understanding the behavior of lightning, by seeking shelter during storms, by avoiding open areas, by staying away from tall objects, by not being the highest point in the landscape, by recognizing that lightning can strike from a clear sky, that it can travel horizontally for kilometers before striking the ground, that it is unpredictable, dangerous, deadly, deserving of respect, of caution, of the awareness that the atmosphere is powerful, that it can kill, that it demands attention, demands respect, demands that you take shelter when the storm approaches. Ball lightning is one of the most mysterious phenomena associated with thunderstorms, reported for centuries but rarely photographed, rarely studied, poorly understood. Witnesses described glowing spheres ranging from the size of a golf ball to a beach ball that float through the air, that pass through walls, that disappear with a pop or a hiss, that seem to defy the laws of physics, that challenge our understanding of what lightning can be, what forms it can take. The mechanism is unknown, the conditions for formation are unclear, and the phenomenon remains at the edge of science, at the boundary between the documented and the legendary, between the physical and the inexplicable. A reminder that the atmosphere still holds mysteries, still surprises us, still reveals phenomena that we cannot fully explain. St. Elmo's fire is a luminous plasma discharge that appears on pointed objects during thunderstorms, creating a blue or violet glow on ship masts, on aircraft wings, on church steeples, on mountain peaks, caused by the ionization of air in the strong electric field that precedes lightning, that creates a corona discharge, a continuous glow that is not lightning but a precursor, a sign that the electric field is strong, that lightning may be imminent, that the atmosphere is charged, ready to discharge. Sailors have known St. Elmo's fire for centuries, have seen it as an omen, as a sign of the storm's intensity, as a phenomenon that is beautiful and eerie, that connects the physical and the mythical, that gives the storm a presence, a personality, a sense of the supernatural. Positive lightning is rarer than negative lightning, but far more powerful, originating from the positively charged top of the thunderstorm rather than the negatively charged base, striking the ground with currents that can exceed 300,000 amperes, 10 times stronger than typical negative lightning, creating longer-lasting flashes, creating more damage, creating the conditions for wildfires, for the catastrophic impacts that a single strike can produce. Positive lightning often strikes outside the main precipitation area, can strike from a clear sky from the anvil of the storm that extends far from the rain, creating the phenomenon of a bolt from the blue, the lightning that appears without warning, without the visual cues of an approaching storm. That is particularly dangerous because it is unexpected, because it strikes where people feel safe, where they do not anticipate the threat. Sprites and blue jets are electrical phenomena that occur above thunderstorms, in the mesosphere and stratosphere, discovered only recently with the advent of high-speed cameras, of observations from aircraft and spacecraft, revealing that thunderstorms influence the atmosphere far above the clouds, far above the weather. Sprites are brief red flashes that appear above the storm, triggered by powerful positive lightning, extending upward to altitudes of 90 kilometers, lasting only milliseconds, visible only with sensitive equipment, creating the realization that the electrical activity of thunderstorms extends vertically through the entire atmosphere, connecting the surface to the edge of space. Blue jets are cone-shaped discharges that propagate upward from the top of the storm, reaching altitudes of 40 to 50 kilometers, creating the blue glow that gives them their name, that reveals the complexity of the electrical environment, the way that energy is transferred vertically, the way that the atmosphere is coupled across its entire depth. Thundersnow is a rare phenomenon, a thunderstorm that produces snow instead of rain, occurring when the temperature profile is cold enough that precipitation falls as snow, but the instability is strong enough to produce lightning, creating the surreal experience of thunder during a snowstorm, of the flash of lightning illuminating falling snow, of the rumble echoing through the cold air, muffled by the snow, creating a soundscape that is both familiar and strange, both thunderstorm and blizzard, a combination that occurs only under specific conditions, that is rare enough to be memorable, to be noteworthy, to be a reminder that the atmosphere can create combinations, can produce phenomena that are unexpected, that defy the usual categories, that reveal the diversity of weather. Heat lightning is not a different type of lightning, but simply lightning from a distant thunderstorm, too far away for the thunder to be heard, creating the silent flashes on the horizon, the illumination of clouds without sound, the visual evidence of a storm that is beyond the range of hearing, that is over the horizon, that is affecting another region, another landscape, another group of observers. The term is a misnomer, suggesting a connection to heat, but the phenomenon is simply distance, is the limitation of sound propagation, is the fact that light travels much farther than sound, that you can see a storm long before you can hear it, that the flashes on the horizon are not a different kind of lightning but the same lightning, just far away, just beyond the reach of thunder. Lightning rods, invented by Benjamin Franklin in the 18th century, are a simple but effective technology for protecting buildings from lightning strikes, providing a preferred path for the current to flow to the ground, bypassing the structure, preventing damage, preventing fires, preventing the catastrophic impacts that a direct strike can cause. The rod is a pointed metal conductor, mounted at the highest point of the building, connected by a thick wire to a grounding system buried in the earth, creating a low-resistance path that attracts the lightning, that channels the current safely to the ground, that has saved countless buildings, countless lives. That represents one of the earliest applications of scientific understanding to practical problems, one of the first technologies based on the physics of electricity, on the understanding of how lightning behaves, how it can be controlled, how its destructive power can be mitigated. Lightning produces ozone, the three-atom form of oxygen, through the dissociation of oxygen molecules by the intense energy of the discharge, creating the distinctive smell that is often noticed after a thunderstorm, the fresh, clean scent that is the smell of ozone, of the molecule that in the stratosphere protects us from ultraviolet radiation, but that near the surface is a pollutant, is an irritant, is a component of smog. The amount of ozone produced by lightning is small compared to other sources, but it is part of the atmospheric chemistry, part of the way that thunderstorms influence the composition of the air, part of the complex interactions between energy and matter, between electricity and chemistry, between the physical and the chemical processes that shape the atmosphere. The beauty of lightning is undeniable. The way it illuminates the night, the way it reveals the structure of the cloud, the way it creates the dramatic fleeting images that have been captured by photographers, that have inspired artists, that have become symbols of power, of nature's fury, of the awesome energy of the atmosphere. But the beauty is dangerous, is a reminder that nature is not tame, is not safe, is not something to be taken lightly, that the atmosphere is a dynamic, powerful, sometimes violent system that can create beauty and destruction in equal measure, that demands respect, that demands awareness, that demands that you understand the risks, that you take precautions, that you appreciate the power while maintaining the distance, the safety, the wisdom to know when to watch and when to take shelter. And as you rest now, as you imagine the distant rumble of thunder, as you feel the tension in the air before the storm, as you sense the electric charge building, you can appreciate the power, the beauty, the danger of the thunderstorm, the way that the atmosphere can transform from calm to violent, from clear to stormy, from silent to roaring, in the space of minutes, in the time it takes for the updraft to build, for the charge to separate, for the lightning to strike, for the thunder to roll across the landscape, in the eternal cycle of energy and release, of tension and discharge, of the electric atmosphere that surrounds us, that protects us, that sometimes threatens us, in the powerful, beautiful, dangerous dance of the thunderstorm. The atmosphere you breathe today is not the same atmosphere that existed a century ago, not the same that will exist a century from now, but a dynamic, changing system shaped by natural forces and increasingly by human activity, by the burning of fossil fuels, by the clearing of forests, by the release of greenhouse gases that are altering the energy balance of the planet, that are warming the surface, that are changing the climate in ways that are measurable, observable, consequential, that are reshaping the future of weather, of ecosystems, of human civilization. The concentration of carbon dioxide in the atmosphere has increased from about 280 parts per million before the Industrial Revolution to over 420 parts per million today, a level not seen in millions of years, a change driven almost entirely by human activity, by the combustion of coal and oil and natural gas, by the oxidation of carbon that was buried underground for hundreds of millions of years, that is now being released into the atmosphere at a rate that is unprecedented in Earth's history, that is faster than any natural process, that is overwhelming the capacity of the oceans and the biosphere to absorb the excess, creating an imbalance, creating a warming, creating the climate change that is the defining challenge of our time. The greenhouse effect is natural, essential, the reason the Earth is habitable, the reason the average temperature is 15 degrees Celsius rather than minus 18 degrees Celsius, the reason liquid water exists on the surface, the reason life can flourish. But the enhanced greenhouse effect, the additional warming from the increased concentration of greenhouse gases, is shifting the climate, is raising temperatures, is melting ice, is raising sea levels, is changing precipitation patterns, is intensifying storms, is creating the conditions for more frequent and more severe heat waves, droughts, floods, wildfires, the extreme weather events that are becoming the new normal, that are challenging societies, that are testing the resilience of ecosystems, that are revealing the vulnerability of human systems to changes in the climate. The warming is not uniform, not evenly distributed. but varies with latitude, with season, with geography. The Arctic is warming faster than any other region, 2 to 3 times faster than the global average, creating the phenomenon of Arctic amplification, driven by the ice albedo feedback, by the melting of sea ice and snow, by the exposure of darker ocean and land surfaces that absorb more sunlight, that warm further, that melt more ice, creating a self-reinforcing cycle that is transforming the Arctic, that is opening new shipping routes, that is threatening polar bears and other species adapted to ice, that is destabilizing permafrost, that is releasing methane, that is contributing to further warming, that is creating a cascade of changes that extend far beyond the Arctic, that influence weather patterns globally, that affect the jet stream, that create the conditions for extreme weather in mid-latitudes. The oceans are absorbing about 90% of the excess heat from global warming, buffering the atmosphere, slowing the rate of surface warming, but at a cost. The warming of the oceans is causing thermal expansion, contributing to sea level rise, threatening coastal communities, threatening low-lying islands, creating the conditions for more frequent and more severe coastal flooding, for the displacement of millions of people, for the loss of land, of infrastructure, of the places where people have lived for generations. The warming is also affecting marine ecosystems, causing coral bleaching, shifting the distribution of fish, altering the productivity of the oceans, threatening the food security of billions of people who depend on the ocean for protein, for livelihood, for survival. The oceans are also absorbing about 30% of the carbon dioxide emitted by human activity, creating a chemical change, creating ocean acidification, the decrease in pH that is making the ocean more acidic, that is affecting the ability of marine organisms to build shells and skeletons, that is threatening coral reefs, that is disrupting the base of the marine food web, that is creating another stress, another challenge, another consequence of the rising carbon dioxide that is changing not just the climate but the chemistry of the ocean, the chemistry of the atmosphere, the chemistry of the Earth system. The melting of ice sheets in Greenland and Antarctica is accelerating, contributing to sea level rise, creating the potential for meters of rise over the coming centuries, creating the possibility of catastrophic impacts, of the inundation of coastal cities, of the displacement of hundreds of millions of people, of the loss of agricultural land, of the salinization of freshwater supplies, of the transformation of the coastlines, of the maps, of the geography of the planet. The ice sheets are massive, containing enough water to raise sea level by 7 meters for Greenland and 60 meters for Antarctica. And while the complete melting would take centuries or millennia, the process has begun. The ice is flowing faster, the glaciers are thinning, the ice shelves are collapsing, creating the conditions for accelerated loss, for the crossing of tipping points, for the irreversible changes that could reshape the planet. The changing climate is affecting precipitation, creating a world where the wet regions are getting wetter and the dry regions are getting drier, where the intensity of rainfall is increasing, where droughts are becoming more severe, more prolonged, more widespread, creating challenges for agriculture, for water supply, for ecosystems, for the billions of people who depend on predictable rainfall, on the seasonal rhythms that have shaped societies, that have determined where people can live, what they can grow, how they can survive. The changes are not uniform, not simple, but complex, variable, creating winners and losers, creating regions where conditions improve and regions where conditions deteriorate, creating the need for adaptation, for resilience, for the capacity to cope with change, with uncertainty, with the new climate that is emerging. The atmosphere has a memory, a record of past climates encoded in ice cores, in tree rings, in sediments, in the isotopic composition of ancient materials, revealing the history of temperature, of precipitation, of atmospheric composition over hundreds of thousands of years, over millions of years, showing that the climate has changed before, that the Earth has been warmer and colder, that ice ages have come and gone, that the climate is not static but dynamic, always changing, always responding to forcings, to changes in solar radiation, to changes in orbital parameters, to changes in volcanic activity, to changes in the distribution of continents, to the slow, inexorable processes that shape the planet over geological time. But the current warming is different, is faster, is driven not by natural processes but by human activity, by the release of carbon that was sequestered underground, that is now in the atmosphere, that is changing the climate at a rate that is unprecedented, that is faster than the capacity of many species to adapt, that is creating the conditions for mass extinction, for the loss of biodiversity, for the transformation of ecosystems, for the sixth mass extinction, the first caused not by an asteroid or a supervolcano, but by a single species, by humans, by the unintended consequences of industrialization, of the pursuit of energy, of the burning of fossil fuels that has powered the modern world, but that is now threatening the future. The future of the climate depends on the choices we make, on the actions we take, on the policies we implement, on the technologies we develop, on the willingness to transition away from fossil fuels, to reduce emissions, to protect forests, to restore ecosystems, to adapt to the changes that are already underway, that are already inevitable, that will continue for decades, for centuries, even if emissions stop today. The climate has inertia, the oceans have thermal mass, the ice sheets have momentum, and the warming will continue. The sea level will continue to rise. The changes will continue to unfold, creating the need for both mitigation, the reduction of emissions, and adaptation, the adjustment to the new climate, the new conditions, the new reality. The Paris Agreement, signed in 2015, represents a global commitment to limit warming to well below 2 degrees Celsius, preferably to 1.5 degrees Celsius relative to pre-industrial levels. A goal that requires rapid, deep reductions in emissions, requires the transformation of energy systems, of transportation, of agriculture, of industry, requires international cooperation, requires political will, requires the recognition that climate change is not a distant threat, but a present reality, that the time to act is now, that the window for preventing the most catastrophic impacts is closing, that the choices made in this decade will determine the climate for centuries, will determine the future of the planet, will determine the world that future generations will inherit. The atmosphere is resilient, has recovered from past perturbations, from volcanic eruptions, from asteroid impacts, from the changes that have occurred over billions of years. But the recovery takes time, takes centuries, takes millennia, and the question is not whether the Earth will survive, whether the atmosphere will persist, but whether human civilization will survive, whether the ecosystems that support us will survive, whether the conditions that have allowed humanity to flourish will persist, or whether we are creating a world that is hotter, more unstable, more hostile, more challenging, a world where the weather is more extreme, where the climate is less predictable, where the future is more uncertain. The study of weather, of climate, of the atmosphere is not just an academic exercise, not just a matter of curiosity, but a matter of survival, of understanding the system that sustains us, that provides the air we breathe, the water we drink, the conditions for agriculture, for ecosystems, for life. The atmosphere is not separate from us, not external to us, but part of us, connected to us, influenced by us, and we are part of it, dependent on it, vulnerable to its changes, responsible for its future. The choices we make, the actions we take, the emissions we release, the forests we protect or destroy, the energy systems we build, all of these shape the atmosphere, shape the climate, shape the future, and the responsibility is ours, the challenge is ours, the opportunity is ours, to create a sustainable future, to protect the atmosphere, to preserve the climate, to ensure that the sky remains a source of wonder, of beauty, of life, for generations to come. And as you rest now, as you feel the air around you, as you breathe in and out, as you sense the presence of the atmosphere, you can reflect on the fragility, the resilience, the beauty of this invisible ocean, this protective envelope, this dynamic system that has shaped the earth, that has made life possible, that continues to breathe, to circulate, to change in rhythms that are both ancient and new, both natural and human-influenced, both stable and shifting in the eternal dance of air and energy, of heat and cold, of the atmosphere that surrounds us, that sustains us. That is changing. That needs our care, our attention, our commitment to preserve it, to protect it, to ensure that it remains for all time the breath of the earth, the sky that shelters us, the atmosphere that is home.